Yes, it's Uncle Jegz. We are now on to the first part of Chemistry 1, which is atoms, elements, and compounds.
Yes, science!
If you need to download my adapted specification, check out the descriptions to check that one. In today's lesson, we'll be going through chemical symbols, how to name chemicals, the difference between atoms, elements, molecules, and compounds, symbol equations, and also half equations. I've highlighted balanced equations because I've already covered that in detail in this previous video over here. Clickety-click the card to teleport over to that one there. So, let's chop some science. Here are the retrieval questions for this lesson. You know what to do. Eukaryotic cells have their DNA stored inside a nucleus. Red blood cells are adapted to carry oxygen around the body. Active transport is not passive because it uses energy to move substances from a low concentration to a higher concentration. Since diffusion and osmosis do not need energy, those two can be classified as passive transport systems. The idea of elements has been around for thousands of years. In classical Eastern philosophy, it was believed that reality was made up of earth, water, metal, wood, and fire. The word element itself comes from the Latin word elementum, which had several translations, but the one we're focusing on is the one that meant the most basic form. So, if you meet someone that's very basic, you can just call them elementum. I want you to have a think about these three questions here. Why do you think people believe this? Would you have believed this if you lived 2,000 years ago? And also, what experiment can you do today to disprove this idea? The modern idea of an element is a substance that's made up of only one type of atom. An easy way to clock if something's an element or not is to just look at your periodic table.
But look at here! Look! Look!
So gold is an element because we have it on our periodic table, and also oxygen. There are just over 100 elements that make up our entire universe. If I were to take a piece of gold and I keep cutting in half, cut in half, cut in half, all the way, the smallest thing that I can have that can still behave like gold will be an atom of gold. This brings us to the definition of what an atom actually is. Atoms are the smallest part of an element that can chemically exist. That means that anything smaller than an atom no longer has the chemical properties of that element. Which of these three boxes is showing the atom? You should all be able to clock that default it is not C. And hopefully you were able to clock that it must have been A because there's only one single particle there, so that must be the atom. You can technically classify A and B as elements because they're both made up of just one type of atom. C is showing a compound. Compounds have two or more different atoms that are chemically joined together. We'll go into detail on chemical bonds in a later lesson. I think we can squeeze another definition in here. B and C are pretty similar in some ways, aren't they? They are both molecules. Molecules are just two or more atoms chemically bonded together. If the atoms are different, it's a compound. If the atoms are not different, it's a molecule, but both of them are molecules. A quick summary of all of that. Atoms are the smallest part of an element that can chemically exist. Compounds are two or more different atoms chemically bonded together. And molecules are just two or more atoms chemically bonded together. So all compounds are molecules, but not all molecules are compounds. Okay, before we move on now, have a go at these challenge questions. All of them are molecules, but only hydrochloric acid and carbon monoxide are compounds. Only oxygen and nitrogen can be considered elements because they are only made up of one type of atom. Let's look back at the periodic table again. We saw from the last slide that carbon monoxide is CO. But have a look at cobalt. We see that the chemical symbol is also CO. So how can you tell the difference between elements and compounds just by looking at the symbols?
What nonsense is this?
Well, you just need to count the number of capital letters that you have. Let's add hydrogen chloride here, or hydrochloric acid. The symbol is HCl. We have two capital letters here, H for hydrogen and the C for the start of the Cl for chlorine. That tells us that we have two separate elements here. Any element like chlorine and cobalt that has two letters always has the second letter in lowercase. So just by counting the number of uppercases you've got, you can clock the number of elements that you have. You need to be able to also name some compounds.
Baby girl, what's your name? Let me talk to you. Let me buy you a drink.
I'll go into more detail when we have a look at ionic bonds and neutralization reactions, but for now I'll just show you some basic steps. Here are some common simple compounds that you need to be familiar with. Take some time to try and name these, and as an extension, write the chemical formula for them. You shouldn't get intimidated with all the detail. You should only focus on the element symbols that you see. For the first one, it's called ammonia, and the correct symbol equation for this is NH3. I've seen the mark scheme allow H3N, but that's not the way chemists write it, so just get used to writing NH3. Then we have water, which is H2O. The third one is carbon dioxide, CO2. The di tells us that we've got two, so there are two oxygens, carbon dioxide. If there was three oxygen, it would be trioxide. And finally, this is hydrogen chloride or hydrochloric acid. When it's a gas, it's hydrogen chloride, but when you dissolve the gas in water, it's hydrochloric acid. When you're naming a compound that is made up of an element on the left hand side bonded to an element on the right hand side, an ionic bond is formed. Again, we'll look at ionic bonds in a later video, but let's just focus on how to name these now. Let me give you an example. Lithium and oxygen will make lithium oxide. Clock what has happened here. The name of the metal, which is the thing on the left, has not changed, but the name on the right has changed into a ide, okay? Here's another example. Sodium and sulfur. That makes sodium sulfide. Alright, now have a go at naming these four chemicals. Magnesium and chlorine makes magnesium chloride. Potassium and bromine makes potassium bromide. Calcium and oxygen makes calcium oxide. And finally, lithium and sulfur makes lithium sulfide. Light work. Magnesium chloride has a chemical formula that looks like this. MgCl2. Why is there a 2 there? What's this small 2 doing here and confusing all of us, eh?
Just prepare to go to hell.
I promise you it's actually very, very simple why this is the case, okay? Watch this. Here are the groups on the periodic table. It goes from 1 to 0, but we skip the block in the middle. Each of these groups has an associated valence number.
It was all a lie. Guys, it was all a lie. She lied.
No, don't start panicking. You don't need to know a mad lot of detail here. Valence just tells us how the atoms bond. Don't worry too much. Honestly, trust me, don't worry too much about it. Just watch what I'm doing, okay? Notice how the group number is the same as the valence number up to group 4, and then it goes down all the way to 0. This is how I like to lay out the steps. First, I like to write down the group that each element is in. Magnesium is in group 2 and chlorine is in group 7. Then I use the valence table to write down the valence of each. 2 for magnesium and 1 for chlorine. The next step, you swap the valence numbers. So 1 goes to magnesium and 2 goes to chloride. And look what we have now. We've got the formula. 1 magnesium, Mg, and then 2 chlorines, or 2 chlorides I should say, Cl2. MgCl2. Alright then, how about lithium oxide? Spend some time to fill this table out. Lithium is in group 1 and oxygen is in group 6. The valence of lithium is 1, the valence of oxygen is 2. We'll swap the numbers around, so 2 is in lithium and 1 is in oxygen. What is our formula? Li2O. Notice that when there's 1, that we don't write the 1 next to it. Now try this one. Potassium is in group 1 and bromide is in group 7. The valence of potassium is 1, the valence of bromide is 1. We swap the numbers around, we still have 1, 1, and what do we have? KBr. It's not K1BR1 because again, remember, if it's just 1, you don't have to write the 1 next to it. Okay, now try this one. Aluminium is in group 3 and oxide, the oxygen, is in group 6. The valence of group 3 is 3, the valence of group 6 is 2. We swap the numbers around, so now the 2 goes to the aluminium, the 3 goes to the oxygen. What is our formula? Al2O3. Here I've got a chemical reaction. Hydrogen reacts with oxygen to produce water. Hydrogen and oxygen are the things reacting together, so they are the reactants. Water is what's being produced, so we call that the product. When a chemical reaction occurs, we have an arrow pointing away from the reactants and pointing to the products. So when you write word equations, you have your reactants on the left hand side and your products on the right hand side of your arrow. So in this example, that's hydrogen plus oxygen, arrow, don't put equals, please don't put equals, hydrogen plus oxygen, arrow, water. A reminder that we've already done this video on how to balance chemical equations. So go and watch that video if you don't understand it. Click the card over here to teleport over there. I won't go into it because I've covered that in great detail in that video, okay? We're going to now look at what half equations are. To understand half equations, I'll go through how they are constructed. In this reaction, we have iron reacting with copper chloride to produce iron chloride and copper. The first thing you need to do is to split the compounds that are aqueous.
Jesus Christ.
Just look carefully, it's not complicated. We've just split the substances that are aqueous, AQ. They're dissolved in water, so the ions split up. The copper chloride splits into 1 ion of copper and 2 ions of chloride. And the ion chloride splits into 1 of iron and 2 of chloride. And it's only these two that split because again, they are the one that are AQ. Next, you have to get rid of the thing that hasn't changed on the left and the right hand side. The 2 chlorides haven't changed at all, so we get rid of those. Those are called, the technical word are spectator ions. They're just watching, they ain't doing nothing. When you get up to here, this is called an ionic equation, alright? Again, I'll cover why the charges are the way they are in a later video. The easiest way to remember this is if something is in group 1, it will have a charge of +1. If it's in group 2, it's got a charge of +2. If it's in group 3, it's got a charge of +3. But then it starts getting complicated when you're using the elements in the middle and also the right hand side as well. But again, I'll cover that in a later video. So here we've got an ionic equation. This is now when we're going to split the equation in half. Literally half equations, we're turning our ionic equation into half. Let's look at iron first. The iron on the left hand side is a regular iron atom with no charge. But then on the right hand side, it has a 2+ charge. To get from no charge to 2+, we must have gotten rid of 2 electrons. Remember, electrons are negatively charged. This equation is the half equation for iron. That's done. Simple. Simples. Now pause the video and see if you could do the half equation for copper. We have the copper that's 2+ charge on the left hand side and the regular copper on the right hand side. That means we must have added 2 electrons on the left hand side to get the neutral copper on the right hand side. In half equations, you don't take away electrons, okay? You're always adding electrons, so you have to just work out, is it going to be on the left or the right hand side? Spoiler warning, you should always add the electron where the positive charge is to cancel it out. Now, based on everything we've done so far, try and complete the ionic equation and the half equations for this reaction over here. First, we split the aqueous compounds. We get rid of our spectator ions. And we are left with our ionic equation. The magnesium goes from the metal as an atom to a 2+ charge ion. So we need to add our 2 electrons where we've got our charges, so that goes on the right hand side. The copper on the other hand has a 2+ charge on the left hand side and the normal copper atom on the right hand side. So it's a 2+, so we need 2 electrons. If it was a 1+, we add 1 electron, okay? Since it's a 2+, we add 2+ electrons on the left hand side. And there we go. Lesson is done.
Fatality.
I know that was a lot of information. My mouth is tired from all that talking. But if you need to go back to any of those, I ain't saying no more. Just check the description to click to where you need to go to. And while you're down there, collect some of the goodies that I've made down there. And I'll catch you guys in a bit.